Okay, all right, guys. So this week we'll be talking about the second method for solving profit maximization problem. So last week we have been already talking about the first method, and now we're talking about second approach. So if you remember, we have talked about what is isoquant. Okay, that is each output level find the least costly input combination that would yield the output level. Now, therefore, we have Y1, Y2, and Y3. Okay, the isoquant tells us how much output can input combination produce. All right. So next thing we need to consider is ISO cost line. Okay. So this is very similar to the budget line we have seen previously. So instead of having PX times X plus PY times Y equals to M, we have the wage rate W times L, which is quantity of labor, plus R, that's the capital rental rate, times K. What is K? That's the amount of capital you're gonna rent. Okay, which equals to the cost, C, okay? Therefore, the slope of this is minus W divided by R. That is minus the wage rate over the capital rental rate, okay? And obviously, on the vertical axis, we have the capital, and in the horizontal axis, we have the labor, okay? So obviously, for the firms, what we want is to minimize the cost, okay? So the direction of the cost function goes is inwards. That means C3 is a lower cost than C2, which is better, and C2 is a lower cost than C1, which is better. So C3 better than C2, C2 better than C1. So the closer a line to the origin, the smaller the cost, which means it's better, okay? So therefore, we can write down the cost minimization problem as we're trying to minimize the ISO cost function, minimize C equals to W times L plus R times K with respect to L and K, such that the function, which is production function F, which is input, which is where the inputs are labor and capital L and K, should be greater or equal to Y, okay? That means our production function needs to satisfy that it's the final output is greater or equal to Y, okay? In other words, the firms want to minimize its production cost by choosing its input, subject to the constraint that the output has to be at least Y units. So that's our requirements, okay? At least our output needs to be Y units. So similar to the, for the consumer preferences analyzed, we want to find the tangency point, okay, or the tangent point between isoquant and isocost, okay? Obviously, to the right-hand side of the area, we have FLK greater or equal to Y. That means we can produce at least Y units of goods. And to the left-hand side, that's the red shaded area, that's the cost less than A. Remember, we want to satisfy that our production is greater or equal to Y, and in the same time, we want to find the input combination which can minimize the cost. Means that we will be having the tangency point A, okay? So how do we specifically find this tangency point A? So we will be having a tangency condition. So this, which is slope of isocost line equals to the slope of isoquant A. If you remember, what is the slope of the isocost line? That's minus W over R, okay? And what is the slope of isoquant at A? That's simply the marginal rate of technical substitution. Okay, we have been talking about how do we derive the marginal rate of technical substitution, which is simply the minus the marginal product of L over marginal product of K. Okay, so therefore we must have minus W over R is equals to minus marginal product of L over marginal product of A. By simply rearranging this, we have W over R equals to marginal product of labor over marginal product of capital, okay? So how do we find this optimal K and L? Remember, the tangency condition only give us one equation. To have to solve for two unknowns here, we need two equations, okay? Remember, this optimal solution must be on the isocost line. And the isocost line is known, right? Which is simply W times L plus R times K equals to C. So now we have two equations. Equation number one, which is tangency condition, MPL over MPK equals to W over R. And we have optimal K and L will be on the isoquant with output level Y, which means this has to satisfy production function equals to Y. So therefore, our optimal a level of labor is simply denoted by LCWRY, and the optimal level of capital is simply K equals to KCWRY. Okay, what do I mean WRY here? They are inputs. Okay, so that's a function where the inputs are W, R, and Y. So therefore, we can derive our total cost function. Our total cost function simply is W times the optimal level of labor LCWRY plus rental rate R times capital, that's optimal capital level KCWRY. Okay, simply we can derive the average cost. Okay, simply that's total cost divided by Y, and the marginal cost, that's the change of C over change of Y. Okay, so therefore we'll be having something else to discuss here, that's return to scales. Okay, if we have decreasing return to scale, that means that our average cost is increasing Y and the marginal cost is above average cost. Okay, so if the marginal cost is greater than the average cost, that's decreasing return to scale. And when marginal cost equals to average cost, that's constant return to scale. And when marginal cost is smaller than average cost, that's increasing return to scale, as we will see in examples later. So our question number one is that we know this production function FLK is L to the power of 1 over 3 and times K to the power of 1 over 3. And we know the wage rate is 2 and capital rental rate R is 1. So W equals to 2, R equals to 1. Okay. So since question C, E, G are the same question with different values, so I want to derive the most general case. Okay. So in this most general case, I will be simply not plugging the values. Okay, I will pre-assume that I don't know the value of W and R. Okay, so I will start with a general Cope-Douglas production function, that's FLK equals to L to the power of alpha and K to the power of beta. And in our case, alpha simply equals to 1 over 3, which equals to beta, which equals to 1 over 3. Okay, but now I will pretend that I don't know. Okay, so the general cost minimization problem now is simply minimizing the cost function equals W times R plus R times K, such that L to the power of alpha times K to the power of beta is greater or equal to Y. And this is simply the production function, okay, FLK. Okay, so the tangency condition tell us that MPL over MPK, that's marginal product labor over marginal product capital, should equals to W over R. And I have known that the marginal product labor and marginal product capital is simply the production function first derivative against L and K. So I can derive them as MPL equals to alpha times L to the power of alpha minus 1 times K to the power of beta, and MPK equals to beta times alpha L to the power of alpha times K to the power of beta minus 1. That's simply the power rule, okay, which equals to W over R. Okay, so therefore I can reduce this equation as alpha times K over beta times L equals to W over R. Okay, why do I want this? Because this will tell me the relationship between optimal level of K and L. Okay, simply RK equals to beta times W over alpha times R times L. Okay, and I'm calling this equation number one. This simply tells me the relationship between K and L. Okay, so by substitute equation one back into the output constraint to find the optimal L, that will be the next step I do. If I understand that my output constraint is simply my ISO cost line, right? And I know my ISO cost line is simply L times alpha equal times K to the power of beta equals to Y. And I know K equals to this thing, right? Beta times W over alpha times R times L. So all I need to do is just plug in, right? So this will become L times alpha times bracket beta times W over alpha times R times L bracket to the power of beta equals to Y. So by simply combining those two terms, as you can see, I have L to the power of alpha and L to the power of beta. So I can combine them, right? By combining them, I have L to the power of alpha plus beta. So this will become beta times W over alpha times R to the power of beta times L to the power of alpha plus beta equals to Y. So by moving this term to the right-hand side, I have L to the power of alpha plus beta will equals to Y times alpha times R over beta times W to the power of beta. Okay. So therefore, now if I'm trying to get rid of the power of alpha plus beta, this is simply L equals to Y to the power of 1 over alpha plus beta times alpha times R over beta times W to the power of beta over alpha plus beta. And this is simply the conditional factor demand for labor, or L star, okay? So similarly to what we have learned last week, so if we know what is L star, which is conditional factor demand for labor, we can use the relationship between K and L to derive the conditional factor demand for capital, right? So since we know K equals to beta times W over alpha times R times L, and by substituting L from the previous answer, which is L equals to this thing, okay? So plug that in. What we have is K will equals to beta times W over alpha times R times Y to the power of 1 over alpha plus beta times alpha times R over beta times W to the power of beta over alpha plus beta. Okay, so as you can see here, this is something that I want to reduce, right? Because this is like way more complicated to work with. So what I want to do firstly is that I want to combine those two terms. Which are those two terms? This one and this one, right? By simply inversing this term, I can get those two exactly the same. What do I mean by inversing? It's simply changing the power of beta to the power over alpha plus beta to minus beta to the over alpha plus beta. So therefore, what's left inside is simply beta times W over alpha times R. So therefore, I can combine those two terms, right? If by combining those two terms, what I got is I'm bringing Y to the power of 1 over alpha plus beta to the front, okay? What I got left is beta times W over alpha times R times beta times W to the power of alpha times R to the power of minus beta alpha plus beta. By combining those two, if you remember, this is simply power of 1, right? So this will become power of 1 minus beta over alpha plus beta, okay? So therefore, I have finally derived that this K star will simply equals to Y to the power of 1 over alpha plus beta times beta times W to over alpha times R to the power of alpha over alpha plus beta. You may wonder, okay, how did this 1 minus beta over alpha plus beta become alpha over alpha plus beta? This is simply because 1 minus beta over alpha plus beta is simply equals to alpha plus beta minus beta over alpha plus beta. So beta minus beta, that would be 0. So this would become alpha over alpha plus beta. Okay. So this is something we call the conditional factor demand for K. Now I have derived L star and K star. Next step, what I would do is to find the total cost. Okay. Remember, what's the total cost function? The total cost function is simply the wage rate times the optimal amount of labor plus the capital rental rate times optimal level of capital. Okay, since I have derived L star, K star, the optimal level of labor and capital before, all I need to do is just plug them in. So this will become W times Y to the power of 1 over alpha plus beta times alpha over, times R over beta times W to the power of beta over alpha plus beta plus R times Y to the power of 1 over alpha plus beta times beta over times W over alpha times R to the power of alpha over alpha plus beta. So straight away, I realized that I have one Y to the power of 1 over alpha plus beta, both to the left and right hand side of the plus sign. So I can simply combine them, right? And moving that to front. So in the front, I have Y to the power of 1 over alpha plus beta, which times W times alpha times R over beta times W to the power of beta over alpha plus beta plus R times beta times W over alpha times R to the power of alpha over alpha plus beta. Okay, so first of all, I realized that this is not simplified enough. Okay, so I have W here and I have W over here. Is there a way I can combine them? Yes, simply just bringing the W out, right? Bringing the W out, this term will become W to the power of minus beta over alpha plus beta, because that's in the denominator. And what we got left is alpha times R over beta to the power of beta over alpha plus beta. Okay, so that's the first thing I'm going to do. How about to the right hand side of the plus sign? To the right hand side of the plus sign, I have R and R. Okay, so can I combine them? Yes, we can. So lifting the R from this one over here, this R will become R to the power of minus R for minus alpha over alpha plus beta. Okay, simply because this is in the denominator. Okay, and the power is alpha to the power of alpha plus beta will become minus alpha to the power of alpha plus beta. Okay, so now I have bring those two terms out. I have just a quick summary. What I have done here is bringing W and R out and trying to combine them. Okay, so let's take a look at W first. So as for the W, this is W times W to the power of minus beta over alpha plus beta. This is simply W to the power of 1 minus beta over alpha plus beta. If we remember, we have derived this previously. 1 minus beta to the power of alpha plus beta is simply alpha over alpha plus beta, right? And we also have this over here, R to the power of 1 minus alpha over alpha plus beta. And this one is simply can be reduced to beta to the power of alpha plus beta, right? So now what we got is over here, y to the power of 1 over alpha plus beta times bracket w to the power of alpha over alpha plus beta times alpha times r times over beta to the power of beta over alpha plus beta plus r times r to the power of beta over alpha plus beta times w over alpha to the power of alpha over alpha plus beta. So again, what I'm trying to do next is that I'm going to combine R and W. Okay, so you realize we have R over here. I can bring it out. Okay, by bringing this out, this become R to the power of beta over alpha plus beta. Okay, and I'm having a W over here, right? I can bring it out. By bringing this out, this become W to the power of alpha over alpha plus beta. Okay, so now as you can see, I'm having W over here, okay, and W over here, and I'm having R over here and R over here. Can I combine those four terms with only one single W and one single R? Yes, I can. So this will simply become y to the power of 1 over alpha plus beta times W to the power of alpha over alpha plus beta. Bring this out from the, realize what I have done is I'm simply bringing this out of the equation, okay? And bringing this out of the equation. Then it's become outside of the equation, right? And I can also bring out this R term out, right? Because they are exactly the same, okay, right? They're exactly the same, those two terms. I can bring them out to the equation. This will become R to the power of beta over alpha plus beta. And finally, what's left in the equation, left in the bracket, is bracket of alpha over beta to the power of beta over alpha plus beta plus beta over alpha to the power of alpha over alpha plus beta. Okay, and now I'm calling this equation number 2. Okay, so remember what we're doing here is really just trying to solve for the total cost. So finally I got it. A very simplified term that is C star y, the total cost, equals to y to the power of 1 over alpha plus beta times the wage rate W to the power of alpha over alpha plus beta times the capital rental rate R to the power of beta over alpha plus beta times bracket of alpha over beta to the power of beta over alpha plus beta and beta over alpha to the power of alpha over alpha plus beta, and that's end of the bracket. That's my total cost function. Remember, what's average cost? Average cost is simply the total cost function divided by y. A function divided by y isn't it same as times y to the power of -1, right? Because 1 over y is simply y to the power of -1. They're exactly the same. So therefore, remember I have this term y to the power of 1 over alpha plus beta over here. Can I combine those two? Yes, I can combine. And this will become y to the power of 1 over alpha plus beta -1. Okay. So what I got left is exactly the same as the total cost function. Okay. These two parts are exactly the same. The only difference is now I have y to the power of 1 over alpha plus beta -1 in front. Okay. Next, I'm deriving the marginal cost. The marginal cost is simply change of the total cost function against change of y, first derivative. So by the power rule, this has only something to do with y, right? And along this equation, let me delete all this. Along this total cost function, there's only one place, one term has something to do with y, which is here, okay? All the rest of them can be regarded as constant multiply rule, okay? So they wouldn't change over there. They'll be exactly the same. So by power rule, what I need to do is simply bringing that 1 over alpha plus beta to the front of the equation, okay? And from the power rule, this will become 1 over alpha plus beta -1, okay? And the rest of the terms are exactly the same as my total cost function. And I'm calling this as my equation number 4. And my average cost is equation number 3, okay? So finally, I have finished derive the optimal level of labor, the optimal level of capital, and so that's for total cost, average cost, and margin cost. Now I can finally get started with the question. Question number A, does this production function exhibit increasing, decreasing, or constant return to scale? How do we verify that? Okay, again, we have done this before in the last week's tutorial. Simply, I multiply both labor and capital by a constant number. Okay, this can be 2, 3, 4, 100, or simply alpha, up to you. But I'm using 2 over here. So this will become 2L to the power 1 over 3 from the production function times 2K to the power 1 over 3. Okay. So by combining 2 to the power 1 over 3 and 2 to the power 1 over 3, this becomes 2 to the power 2 over 3. Okay. Times L to the power 1 over 3 times K to the power 1 over 3. This will become 2 to the power 2 over 3 times the production function. Okay. Which is smaller than strictly timing 2 outside the bracket of the production function. So if this is smaller than 2 times the FLK, this is something we call decreasing return to scale. Remember, if this is greater, then it's increasing return to scale. If it's equal, then this is constant return to scale. Okay, that's pretty easy. Level B, we need to find the total cost, average cost, margin cost. And if average cost increasing or decreasing, why is the margin cost higher or lower than the average cost? Okay, that's pretty easy. Okay, because we have derived all that useful solutions, results that we can use from above. For example, we have derived K star over here, and we have derived L star over here, okay? And we also know total cost is this, equation 2, and we know equation number 3, that's average cost, and equation 4, that's marginal cost. So all we need to do is just plug in numbers. Okay, let's do that. Here, I know alpha equals to 1 over 3, beta equals to 1 over 3, and some useful constants that we can calculate is 1 over alpha plus beta is 3 over 2. Alpha over alpha plus beta is 1 over 2. Beta over alpha plus beta is 1 over 2. Okay. And firstly, we have alpha over beta to the power of beta over alpha plus beta, and beta over alpha times to the power of alpha over alpha plus beta. That's simply 1 to the power 1 over 2 plus 1 to the power 1 over 2, which equals to 2. Okay, that's pretty easy. That's simply square root of 1 plus square root of 1 means 1 plus 1 equals 2. Okay, so using equation 2, 3, and 4, and plugging the value that W equals to 2, R equals to 1, we can get that total cost, which equals to Y to the power 1 over alpha plus beta, is simply Y to the power 2 over 3. Okay, and W to the power of alpha over alpha plus beta, that's simply 2 to the power 1 over 2. And r to the power of beta over alpha plus 1, that's 1 to the power of 1 over 2. And this term, the last term in the bracket, we have derived over here, right? It's simply equals to 2, okay? So this will become 2 times square root 2 times y to the power of 3 over 2, and this will be my total cost, okay? As for the average cost, we can use our equation number 3, right? That is simply 1 y to the power of 1 over alpha plus beta minus 1. That's y to the power of 3 over 2 minus 1. That's simply y to the power of 1 over 2, okay, or square root of y. And again, this w to the power of alpha over alpha plus beta, that's simply 2 to the power of 1 over 2. And our r to the power of beta over alpha plus beta is 1 to the power of 1 over 2. And again, the last term, the bracket term, is something we have calculated over here, which equals to 2, right? So this would become 2 times square root 2 times y to the power of 1 over 2, okay? Next, we calculate the marginal cost. The marginal cost is 1 over alpha plus beta, which is 3 over 2, times y to the power 1 over alpha plus beta minus 1. And this will simply be y to the power 1 over 2, okay? Square root of y. And w times to the power of alpha over alpha plus beta, that's 2 to the power of 1 over 2. And next we have r to the power of beta over alpha plus beta, that's 1 to the power of 1 over 2 square root of 1. And lastly, we again have the bracket term that's equals to 2, okay? So this will become 3 times square root 2 times y to the power of 1 over 2. So what we can see here is that obviously that our marginal cost is greater than the average cost, right? That's some useful results that we can use. Remember, whenever the marginal cost is greater than the average cost, this is something called decreasing return to scale, right? Decreasing return to scale is exactly what we have proved in question number 8, right? That's interesting. This tells us there are actually 2 ways to prove something is decreasing, increasing, or constant return to scale. Number 1, by multiply by a constant number. Number 2, just compare the marginal cost and average cost, okay? So, and plus, since we know the change of average cost against change of y, that's simply first derivative of average cost, equals to 1 over 2 times 2 times square root 2 times y to the power of minus 1 over 2. Because all those terms are positive, so therefore this is positive number. If the first derivative of average cost is greater than 0, we know the average cost is increasing in y, okay? And point number 3, I have already talked about that marginal cost 3 times square root 2 is greater than 2 square root 2, which is AC, okay? MC greater than AC, MC is higher than AC for y, which means decreasing return to scale, okay? So that's question A and B, A and C. So now next, find the total cost of producing 32 units of output. We have already calculated the total cost function over here, right? 2 square root 2 times y to the power 2 over 3. Simply plugging over here by letting y equals to 32. So this will be 64 to the power of 3 over 2, which equals to 512, okay? That's pretty simple. Now we consider the production function has changed to FLK, L to the power of 2 over 3, K to the power of 1 over 3. So I'm telling you a trick over here. If I'm looking at my Cope-Douglas production function, that where alpha plus beta is smaller than 1, okay? This is guaranteed decreasing return to scale. Okay, because 1 over 3 plus 1 over 3, 2 over 3 is smaller than 1, that's decreasing return to scale. I'm telling you the third way, but this is not official way, okay? Just a simple trick for you to confirm your results. And for our second case, alpha equals to 2 over 3, beta equals to 1 over 3. So therefore, alpha plus beta equals to 1. Therefore, I will suspect that this will be constant return to scale. But is it? Let's check, okay? The same results as before, same method as before. Multiply the labor and capital by 2, okay? Simultaneously. This will become 2L to the power 2 over 3 times 2K to the power 1 over 3. And obviously 2 to the power 2 over 3 plus 2 to the power of 2 over 3 plus 1 over 3 is simply equals to 2, right? Then this will become 2 times FLK, which is exactly equals to 2 times FLK. And this is something we call constant return to scale. Yeah, indeed. See, I told you for Cope-Douglas function, if alpha plus beta equals to 1, it's a constant return to scale, okay? But don't use this to answer your question. This is just a trick that you can verify your answer, okay? And question E, find the total cost, average cost. Exactly same thing as before. The only thing different here is alpha equals 2 over 3, beta equals 1 over 3. So again, we calculate those 4 terms, 4 constants. 1 over alpha plus beta is equals to 1. Alpha over alpha plus beta, that's 2 over 3 over 1 over 3 plus 1 over 3, that's 2 over 3. And beta over alpha plus beta, that's 1 over 3, 1 over 1, that's 1 over 3, okay? And the term in the bracket is alpha over beta to the power of beta over alpha plus beta over alpha to the power of alpha over alpha plus beta is simply to the power of 1 over 3, 1 over 2 to the power of 2 over 3, okay? We don't have to calculate this yet, just leave it as it is for now, okay? So next we derive the total cost. Now I know the wages 2 are equals to 1. So y to the power of 1 over alpha plus beta, we know alpha plus beta equals to 1, right? So this will simply equals to y. Okay, next we have w to the power of alpha over alpha plus beta is simply 2 to the power of 2 over 3. And next we have the r to the power of beta over alpha plus beta, that's 1 to the power of 1 over 3. And the bracket term, finally, it's exactly this one, okay? 2 to the power of 1 over 3 plus 1 over 2 to the power of 2 over 3, okay? So by simplify this, what we have is 3 times y, okay? That will be my total cost function, 3 times y. How about my average cost function, okay? Remember, you can either use equation 3 or simply because our total cost function is already so easy, so I don't want to use any shortcuts anymore. I can just use the proper definition that average cost equals total cost divided by y. 3y divided by y, which equals to 3. So it's telling me average cost is a constant number. So therefore, average cost is not increasing, decreasing against change of y, okay? Has nothing to do with y. Again, as for marginal cost, I can use equation 4 if I want, but I prefer not to because my total cost function is so easy. So it's simply the first derivative of 3y against change of y, which equals 3 again. So now, since AC average cost equals to 3, which is a constant number, so the average cost does not depend on y at all. Okay, and since we have marginal cost equals to the average cost, this is telling us constant return to scale. Why? Because we know this from lecture slides that whenever marginal cost equals to average cost, we have constant return to scale. Again, this verified my pre-assumption that alpha plus beta equals to 1, then it's constant return to scale. That's pretty easy, okay? So next question. Now we need to consider where alpha equals to 2 over 3 and beta equals to 2 over 3. So therefore, alpha plus beta is greater than 1. So I'm assuming that this will be increasing return to scale because alpha plus beta greater than 1. But is it? Let's verify that, okay? So again, what we need to do is 2 times L, 2 times K, doubling the inputs, both of the inputs, okay? So this will become 2L to the power of 2 over 3, 2K to the power of 2 over 3. So become 2 to the power of 4 over 3 times L to the power of 2 over 3 and K to the power of 2 over 3, which is exactly FLK, okay? So this will become 2 to the power of 4 over 3 times production function, okay? Obviously, this is greater than 2 times FLK because 2 to the power of 4 over 3 is greater than 2, right? So if that's greater, that's increasing return to scale. Again, bam, that reconfirms that if alpha plus beta greater than 1, that's increasing return to scale. Again, don't use these methods as your answer. I want to say that you're using this, okay? Don't use a shortcut. This is just for verifying your answer purpose, okay? So find the total cost, average cost, and the marginal cost. Again, all I need to do is just change the inputs, right? Change the alpha equals 2 over 3 and beta equals 2 over 3. Now 1 over alpha plus beta is simply 3 over 4, and alpha over alpha plus beta is 1 over 1, and beta over alpha plus beta, that's 1 over 2, okay? And again, the term in the bracket, that's simply 1 over 1 square root of 1 plus square root of 1, that's 2, okay? So now I'm using equation 2, 3, and 4 that I derived in the beginning of this tutorial, and I'm plugging in that W equals 2, R equals to 1 to find my total cost, average cost, and marginal cost, okay? So as for my total cost, easily y to the power of 1 over alpha plus beta, that's y to the power of 3 over 4, and w to the power of alpha over alpha plus beta, that's 2 to the power of 1 over 2. And as for r to the power of beta over alpha plus beta, that's 1 over 1 over 2 square root of 1. And as lastly for the bracket term, we have derived that as equals to 2. So I'm just letting it to be 2. So the total cost now equals to 2 times square root 2 times y to the power of 3 over 4. Okay, that's my total cost. Again, when you're calculating the average cost, you can simply divide by y, but since I have derived my equation number 3, so I'm just going to use equation number 3. That is saying that my average cost equals to y to the power of 1 over alpha plus beta minus 1. That's y to the power of 3 over 4 minus 1, or y to the power of minus 1 over 4, okay? And I also know that w to the power of alpha over alpha plus beta, that's 2 over 1 over 2. And r to the power of beta over alpha plus beta, that's 1 over 1 over 2. And the final bracket thing, okay, that's equals to 2 from the result that we have got. So this will become 2 square root 2 times y to the power of minus 1 over 4. Lastly, we calculate our marginal cost. Again, the marginal cost is calculated as 1 over alpha plus beta, that's 3 over 4, times y to the power of 1 over alpha plus beta minus 1, y to the power of minus 4, 1 over 4. And again, the rest of the term are exactly the same as before. So that's 2 to the power of 1 over 2 times 1 to the power of 1 over 2 times 2. Okay, so this will become 3 over 2 times square root 2 times y to the power of minus 1 over 4. So can we say, is the average cost positive or negative? Okay, it's very easy to say, right? Our change of average cost over change of y is simply minus 1 over 4 times 2 to the square root 2 times y to the power of minus 5 over 4, which is smaller than 0, okay? Because we have bringing minus 1 over 4 to the front, right? So we have this. There's a minus sign, therefore it's smaller than 0. So we know average cost is decreasing in y, okay? Next, we compare marginal cost and average cost, okay? So we have calculated marginal cost equals to what? 3 over 2 times square root 2 times y to the power of minus 1 over 4. And we have calculated the average cost as 2 times square root 2 times y to the power of minus 1 over 4. So we know marginal cost is smaller than average cost. So that means that our average cost greater than marginal cost, which is increasing return to scale, right? Exactly the confirmation as our assumption before. That's question A, okay? This might look a little bit complicated, okay? So what the trick here is that if you have used or derived this general results in the beginning of the tutorial, then this is much easier, right? You can just use the results and plug in the values in, okay? I'm not too sure if you can use those results in your assessment, okay? I'm pretty, you probably need to check with PMREC, but I assume that you can use these results, okay? Remember, this only applies to Cope-Douglas production function. You cannot use this to other production functions. For example, our question number 2, we can't use it anymore, okay? So this is minimizing S and L over 4. They are which means the inputs are substitutes, okay? And we know that as a result, if the inputs are substitutes, we always have a constant return to scale. Why? Because you can shuffle around S and L, okay? You can shuffle seat and legs, okay? So does this production function exhibit increasing, decreasing, or constant return to scale? I know there's always constant return to scale, but it's better to verify, right? So same, excuse me, same method as before, F to S to L. So the hint is saying that minimize of 2x to y equals to 2 times minimum x and y. So therefore, function 2s to L, it's simply 2 times minimum s and L4, which means it's 2 times production function. If doubling the input is doubling the output. This is something we call constant return to scale, okay? This is due to we have a minimizing function, okay? Minimizing function, you can always bring in the constant out, okay? Question B, suppose the seed costs $5 while leg costs $1. Find the total cost, average cost, and margin cost, okay? So we need to understand, to make one chair, we need one seat and 4 legs. This is very similar to the case that we previously discussed that you need to pair one ice cream with one corn, right? When you're producing a chair, you need one seat and 4 legs. Otherwise, your seat will be not stable, okay? So since each seat costs $5 and each leg costs $1, the cost producing one chair must equals to 5 times 1 plus 1 times 4, right? $5 seat times 1 and $1 legs times 4. So producing 1 unit of the good will cost you $9. So given that we have constant return to scale, so no matter how much more production you produce, the cost will be exactly the same. So therefore, my total cost is simply my quantity times the cost that producing one chair, right? The cost producing one chair times how many chairs I'm producing. That's simply 9 times Y, okay? Average cost is simply the total cost divided by Y. So 9Y divided by 9Y, that's 9. And marginal cost is first derivative of total cost, okay? 9Y is first derivative against change of Y, that's equals to 9. Again, average cost equals to marginal cost. That's telling us this constant return scale. So again, the key point here is you need to understand whenever we are producing something that their inputs are substitute goods, okay? Perfect substitutes. Perfect complements good, okay? Perfect complement goods, S and L. And you have a minimization function. You will always have constant return to scale, okay? I apologize, they are complement goods, okay? So that's all for this week's question. I will be still running my consultation this week. So if you do have any questions or if you want to ask me anything, come to my consultation this week or next week. Okay. I hope all of you guys have a great weekend. Thank you. Bye.